Go ahead, Jan.
Thank you. So good afternoon, everyone. Thanks the organizers for letting me speak online in this rare circumstance. So my name is Jan Brandejs. I am a postdoc in CNRS recently switched from a quantum physics chemistry lab to a computer science laboratory, and it's called IRIT in Toulouse, both of them in Toulouse. So I will present you TAPP, the Tensor Algebra Processing Primitives. That is a standard for tensor operations developed by me and the TAPP working group. So what I mean by the TAPP working group, that's a standardization working group. That's where there's multiple participants, but I will just list those that are the most active in terms of code contribution. So that's Edward Wallace from Virginia Tech, who developed a well-known block sparse tensor contraction library called tiled array. Then Devin Matthews, who developed his own tensor contraction library called tbliss, and Paul Bentinesi, and a machine learning, and a HPC expert from Sweden, and his student Niklas, and then hardware vendors Alex Heinecke from Intel and Jeff Hammond from NVIDIA. Then this is joined by the feedback from the TAPP community, which was built on 2 workshops that we had in Toulouse on the topic, and open government style in the TAPP working group means that everybody is welcome to join. So what do I mean by a tensor contraction? I think I don't really have to tell you, but I just want to make sure to set the terms right, because we found that actually everybody uses different terms for, calling in a number of indices. Could be a rank in some community, a dimension in the other community, or just a number of modes.
Yeah, you just wait a bit. We have a problem here with the
Yes.
computer.
Okay, that should be. Jan?
Can you
Okay.
try it again? Yeah. Okay.
Yes. Can I continue? Okay.
Yes, please. Yeah.
So you all know a familiar case of a matrix product with two index tensors being contracted over a shared index k, which can be depicted like this as a diagram in on the right hand side. You can see how it's depicted as a tensor network diagram, and this can be generalized to tensor trains or matrix product states, and tree tensor network, for instance, and PEPs, meta, and other concepts. This is what I worked on during my PhD in Prague, and then I switched on working on couple cluster theory, where the 2 workhorse contractions that are arguably the most important are those 2. So on the left, you can see this 2 four-index tensors being contracted over 2 indices C and D, and then the other right next to it, again, four-index tensors being contracted over 2 indices, but different 2 indices. So it looks like the same on the diagram, but in fact, there's a difference between this, because the one on the left can be formally represented as a matrix multiply if you join together indices C and D and B and IJ, whereas the other one cannot. So what I mean is that if you store your tensors in some standard way, sort of like in a column major, row major format, then the contraction on the right hand side cannot be written as a matrix multiply unless you do some reshuffling of elements in the memory. So that means you'll maybe want to use some tensor library that can do this, or you would just simply do the reshuffling in the memory. So TAPP, why do we need TAPP? Is because for matrices there is BLAS. Everybody who writes high-performance code knows about BLAS, and that consists of a specification. That's like a technical specification of the interface. Then it's reference implementation, and there's multiple very highly optimal implementations available, including MKL, for instance. And then it is interfaced to multiple languages like Fortran, C++, and others. It has open governance and high-level consumers like libraries like LAPACK or languages like MATLAB, for instance, permissive licensing. And for tensors, there is simply nothing. There is no BLAS for tensors for the moment that would be used by the entire community, and that would create sort of open market for implementations of tensor tools. So why is that? It's because there's too much freedom, too many parameters in the types of operations and how they can be implemented and optimized. So we try to map it, for instance, for the case of DMRG, and we created a survey, contacted 37 packages, authors of 37 packages of DMRG, and mapped on which numerical software they're using. And the situation is not sort of as nice as we would like, that people would join using the same thing. There's several dispersed communities, and still new and new like code duplication effectively because people reinvent the wheel and build a new that just does the same thing as the existing software. So what happens, like what led me and our team in Toulouse to work on this, is that we had this quantum chemistry package, Dirac, and we wanted to use some distributed memory tensor library to use many nodes on a supercomputer. So we rewrote our code base to be able to use it. Then after a few years, the developer of the library left to NVIDIA and left us basically having to rewrite the code base again to use a different software. And we wanted to stop this and be able to switch between different backends for tensor operations easily. And the idea is to create some tensor primitives that you can build your application code once and then reuse it across code, share it across community, and facilitate reuse of software and also interfacing of softwares between. So yeah, this is just about the survey that you can find on this archive link about the DMRG. So basically, the idea is we should try to share to avoid code duplication. So how we design a tensor contraction interface, in fact, it's different than for matrices, because in BLAS, you have a different name for every operation, like SGEM, DGEM, and then there are many other operations that you can do. In tensors, you cannot do this because there's simply too many. And the way we solve this is that we first create some sort of metadata structure called tensor info that describes a tensor, then a similar descriptor for a tensor operation. So for instance, create tensor product, and then separately execute to product. There's some performance reasons for this. And the idea here, we wanted to create the correct encapsulation that actually captures what is optimal for implementations and sort of user-friendly, what as much as can be for a C API. So the reason why we used C language is that it's the most portable that we can think of, and you can use it easily from Fortran, C, C++, Julia, Python, and others. So TAPP itself is an interface. It's an interface standard. It's not really like trying to create the most optimal code to run this super fast. Like, it's an interface that allows you to use that super fast code that already exists. So there are existing libraries, or you can write your own, but the TAPP provides a glue to let you use those. And it's not really a domain-specific language. It doesn't try to capture all possible operations with your data. It just captures several important operations, and then you can do other things with your tensors as you like. So, for instance, apply phase operator separately from TAPP. We thought it would be very easy to develop this, but it turned out it took 2 years of regular meetings of experts with really a lot of cross-field experience included. It wasn't really possible to develop it without that, because it's easy to develop some tensor interface, but it's actually hard to create a good and sustainable tensor interface that will be used across domains. So, as I said, TAPP offers the specification. There's a white paper on arXiv, operation taxonomy, defining different types of tensor operations and which should be supported, which are, for instance, optional, and then a reference implementation that everybody can check the correctness. Then a lot of automated randomized tests, which there's code that creates all possible random tensor contractions and number of indices, different extents, and then checks that for instance, 2 different libraries give you the same numbers. And it provides benchmark examples based on what we collected from the community in a survey, and then bindings. That means it's an interface to existing tensor libraries. So tbliss for CPU, qtensor for GPU, hiptensor for AMD GPUs, then qblas and hipblas when you are willing to do the permute of data, and then even distributed memory tensor contraction library Cyclops, which is known for its anti-symmetry support. So, index permutation symmetry. What is really nice about TAPP is that once you use it, it can happen that the developer of the tensor library will themselves bind their library to TAPP. Or for instance, that happened to me. I had my code using TAPP, and Devin Matthews, who has this tbliss code, himself interfaced it with TAPP. So I suddenly get access to another tensor library without having to do anything, which is really nice from the user standpoint. Also, he maintains the interface, and I don't have to worry about that as a user. So TAPP also went to a bit more advanced use cases like asynchronous execution, when you, for instance, run several tensor operations at concurrently on different streams on one GPU, or multiple GPUs, CPUs at the same time. It allows you to load multiple tensor libraries or tools at the same time on the runtime. So before your start of the program, you don't have to know which library you want to use. For instance, I start my program, I found that I want to use block sparsity, so I will use some implementation that supports that. And I can decide after the start of my program, because the interface is binary compatible. So because there is a clear binary interface defined, you can decide even after startup that you will use some library for something. So it's tested very well. So it's randomized testing even found a bug in qtensor itself, because we explored all the different edge cases and they haven't had everything covered. So even if you want to do something different that is part of the basic TAPP, you can do it and generalize it. It's better to perturb something solid than to start over. And this is the basic call that is standardized in TAPP. It's something that we started with. It's very similar to BLAS for dgem operation. So you have 2 tensors A and B contracted with some index sets. I just say that there's some indices here. And these are scaled by scalar alpha. And you add some tensor C. So typically you would see that C and D are the same thing as in BLAS for dgem. But in fact here, we support also different C and D. So it doesn't have to be in addition to the same tensors before. It can be addition to different tensor in some cases. So this is very similar to dgem. To be able to run it, you just create the tensor metadata, then tensor product metadata, and then you execute such that the library can plan before it runs the operation itself. This is what's done typically on GPU libraries or whenever used just-in-time compilation. So as I said, you can write your code in a way that it doesn't even know which library will it use before it runs. So this code, for instance, I'm giving it path to two different TAPP implementations, a reference implementation and qtensor, and it compares the numbers from those two things. So this is what you can have as well. You can ship your application code to users, and then same as with Blast, they will just provide the path to MKL or something without really without you having to worry about it. So this github.com/tapp.org is our official GitHub organization where you can find all the resources, examples, and sort of tutorials how to use TAPP. But it's very easy to start. If you ever used Blast, then it's very similar in some sense. These are two Tensor workshops that we organized in Toulouse to make this happen. We really managed to get all the important industry players, most of the important Tensor library developers, and many important users. And there we shared how to create the interface. We created teams between 6 to 8 people to try to really discuss things and resolve the most painful issues. It turned out this was efficient, so we were able to agree on something. And in the end of the first workshop, we already had some basic code. So these were standardized later on during the many working group meetings that typically happen once per month. And here, for the workshops, we had sponsors Secam and NanoX, which are very kind to continue support to this effort. And of course, there were some challenges on the way. So, for instance, many different stakeholders want many different features, and I myself, for instance, was pushing for distributed memory to be able to use MPI-based implementations. Then there are people who need TensorFlow structure or tensor networks as a primitive. And that's a bit different. So we needed to start with something simple, and we still started with a single node, so one computer node, dense tensors, and not the entire set of operations which are described in Python einsam or NumPy einsam. We started with a subset of this. And we did that very nicely. And I think we are in a situation now where we are moving to the tensor structure and to distributed memory, because now actually we have a branch which uses distributed memory, and we have a new working group on block sparsity and index permutation symmetry that is finalizing the first block sparse tab. That's also why I'm talking here, because I want you to express your opinions to that and connect with us, and join that working group if you're interested in, implementations of symmetry with tensor networks and having a solid shared interface for that operation. Here's something about the classification of operations which you can do with tensors based on the index sets that you have in the first and second tensor. This Venn diagrams describes two different cases that you can have, and then correspond to different operations, and we define clearly which are required or which are optional, and this you can find in our white paper on archive. There is more to when you go to these multiple libraries at the same time and so on. There were some challenges with that. For instance, handling errors. If you don't know which library is throwing them before you run, it's not always simple, but we managed to find a way. So now we have unified error handling in a way that you get some error codes and error strings that you can show if something goes wrong. So in a tensor network diagram, TAPP standardizes the binary contraction, binary tensor operations. That is something that happens between two nodes here. There could be multiple edges contracted, for instance. And that's the very start. So it doesn't tell you in which order you should do your contractions. It's something like BLAST. BLAST doesn't tell you in which order should you do your matrix multiplies, but it provides the primitive for that. So it's really like the lowest level link to the tensor libraries. And we, in the block sparse standardization group, so that's the second working group, are now working on something more than that, and trying to, for instance, define how a tensor network should be represented. If somebody needs to, for performance reasons, pass that information to some software. But for the moment, even the existing codes, shouldn't use BLAST to directly to formulate tensor operations, but to have the right encapsulation for performance and modularity. There needs to be a tensor BLAST. So for now, we are finding out what to do. We had this tensor survey for the high-level standardization, as I mentioned. So building something on top of TAPP, and there we had 85 participants from different like tensor software applications and libraries, and we managed to really survey this nicely to find out which way should the standard develop. And you can see the results here if you're interested on this DOI. Interestingly, there were very, very diverse communities involved, and we learned that, for instance, even just for instance, block sparse like tensor distribution, or like distribution of block sizes, plays an important role in how you formulate the interface and optimize the implementation. So that influenced how the interface develops. So you should use TAPP Azure because there's the right encapsulation for the operations, as I mentioned. What happens in our case, for instance, we had a PhD student working on tensor software, and he spent the first half year basically writing the framework part, so basically the API. And now it's no longer necessary. You can have a clearly defined tasks, because you can have people focus on the performance optimization and not reinventing the wheel with writing the interface. So in my own case, with the direct package, I managed to rewrite. It was during a hackathon with colleagues. We managed to rewrite in 2 days our code base, like not really rewrite, but just to do some modifications that were hidden in TAPP, to use emulation, that is variable precision, or the Osaka scheme. And we get that working in 2 days for our entire code base. So that was pretty nice, in my opinion. And we managed to speed up and beat the speed of SQTensor in some cases. And for parallelization from single node to 1,000 nodes on a fastest computer at the time, that was Frontier. It took me 1 week to develop this, because I had the code with TAPP, so I was able to port this distributed memory library, and in 1 week I had the same code running on 1,000 nodes. So please consider joining the discussion. And to conclude, of course, we found that this limited scope is very important to start with. There's a very simple workflow to adopt TAPP if you're interested. And if you're not interested in adopting, just in discussing implementations, or sharing experience on how you think block sparse or GPU distributed codes, for instance, should look like, or which ones you're using, and what features do you request from the routers. Please join us, because we have many of those people on board, and they are actually actively discussing with us. So the idea is to build it once, build your application code once, then reuse it with the others, share across the community, and have a sustainable code without code duplication. So thanks for your attention, and I'm open to any questions.
Question? Sorry. So I have a question about symmetric tensors. Do you have a special treatment of this structure? Do you have compressed representation, efficient computation with symmetric tensors?
And that's a great question. So for so on the interface side, you can work with compressed metric tensors if the implementation supports that. So the TAPP itself is just the interface. So if you're using a library like I don't know if iTensor, for instance, supports this, then if you're using a library that supports that, then you can easily do this, and you can have a tensor which is stored in compressed form, for instance. So your metric tensor. How you could do this is you can pass there's some key value store, and you can pass some context to the library. They have some special feature like this, and the tensor can be compressed, and then the library just if it supports that feature, it can, when it contracts the tensor, use that information. So yes, it will work if your implementation does it. For the moment, I don't think that any of those implementation really supports that. Those that are already included, because they are more low level typically for dense tensors. But we are in fact in talks with Julia people and people from Flatiron to start to integrate with their code. So I think that could be actually a really nice question for them to include this.
Thank you.
Thank you.